Hello everyone. I work in an embedded company where I'm doing security research, IoT devices and programming. We are developing the prevention solution made specifically for smart devices. Today I'm introducing my plugin for IDE Pro Hexray Spy tools, and I hope you will find it as useful as I do. We're going to talk about reverse engineering challenges, about which tools there are to overcome those challenges, and then I show what new is brought by my tool and how it can be helpful. I'll tell you about its features and how to apply them in real-life use cases. Also, I'll introduce API my plugin offers and finally speak about my plans for developing it in the future. As reverse engineers, we must keep a lot of information in our brain when we are doing our work. Understanding what a piece of code does requires a great amount of short-term memory, and to me, it is better to store that information inside instruments. Usually we work with disassemblers and decompilers. And disassemblers allow us to store variables names, create new structures types, and turn numbers contained in disassembly instructions into structure members. However, disassemblers have too many details. However, disassemblers have too many details, and to do modifications using the output is too tedious and laborious. Decompilers create C-like pseudocode abstraction over disassembly. Unlike other products, Hexray's decompiler allows us modifications of its output, so it's a lot simpler to do reverse engineering. It is possible to transform Hexray's output to representation natural to a programmer, and that's far more difficult to accomplish when working with a disassembler. Besides, those modifications can be applied faster than through disassembler. But Hexray's decompiler is not devoid of drawbacks. Sometimes it produces errors by skipping some branches or being unable to decompile at all some functions. It may mix up signed and unsigned types, and so it requires checking up with the disassembler. Also, its output may be very complex. Although decompilers are quite useful, they are not helpful in understanding data or organization. I suppose that understanding how data entered into the program and how they are modified during runtime is a cornerstone of reverse engineering. To understand it, we usually have to take two steps. First, extract data types interesting for our purposes, and second, understand how they are organized. Hexray is not of much help to us. In its output, we see just variables, casts, offsets, or indices, something similar to structure, but not something that can be really used as it is. Also, when we research object-oriented code, we have virtual tables and virtual functions which make the picture more obscure. Here you can see an example of an object-oriented code, and it is not easy to understand what's going on here even after looking into it for a while. However, there are some solutions to these problems, such as well-known plugin Hexray's Code Explorer by Alex Matrosov. Among many features that it has, it allows to find and create virtual tables. Also, it helps to automatically reconstruct structures, but within boundaries of one function body. If we have a big structure, then the results will be far from complete, and we cannot affect the creation process in any way. There was such a plugin as Hexray's Tools. The great thing about it was that it allowed an interactive reconstruction. The user could scan structure pointers and collect information about potential structure members, and then turn that information into structure declaration. However, the author stopped developing it for the new versions of IDE. And my plugin is partially based on this one. Both these tools help to reconstruct structures, however, the results they produce may be far from complete, and they don't help to understand how structures are organized. Another way to deal with reverse engineering challenges is to write your own tools, since Hexaray's decompiler has huge API and can satisfy any requirements for plugin development. That's the way I chose. However, I stumbled upon many issues. Hexarray is notorious for poor documentation, and the best way to find some useful functions for me was to search using regular expressions through header files. Hexaray's API is constantly changing, and it is normal practice to not give recommendations about what new methods use instead of deprecated ones. API is wheels within wheels, and for example, changing type of argument in one function requires 80 lines of code and 3 classes. There are some useful functions like notify available for C++ that allow to make useful callbacks, and it is not existent in Python bindings. Also, there are a lot of unobvious things. For me, the most painful was to understand why IDA crashed after C3 modifications. I spent several days, and turns out that I should have disabled Python garbage collector for these weak objects. So here is the picture you should be ready to see very often if you decide to start developing Hexarray IDA Pro plugins. Nevertheless, I've managed to create a solution which helps me quite a lot in my work, and I hope it helps other people too. As I said, it is based on Hexarray tools, but it has gone much further and is doing much more than the original one. Hexarray's PyTool is written on pure Python, so it's simpler to maintain and develop, and it supports all operating systems. Especially for Insomnihack, I released a new version, and today I've updated my GitHub repository. The new version was mostly used by me and internally in our company, and it is more advanced than the public one. So let's talk about what benefits my plugin gives. And we start with structure reconstruction. Imagine that you have big or not very big structure that you want to reconstruct somewhere in your code. What would you do? Probably take a piece of paper or open Notepad and start digging through the code, searching for references to different members. And those references are represented as offset or indices. After collecting enough information, you turn that into type declaration. Input the declaration into local types and then proceed to apply the new type to variables which are pointers to this new structure. Quite exhausting work, I would say, especially if there are a lot of structures in your code. And now I show how we can automate this process by using the shallow variable scanner and the structure builder features of my plugin. Here is a code from the web server of an embedded device that I research in my work. And here you can see a sprint function that one would like to explore due to its unsafety. That a sprint copies character string from one structure member to another. In order to understand how data get there, we should reconstruct structure and understand what members are made for. Here you can see referenced members of some structure, and we can see that this structure has members at offset 90,000, which is quite a lot, and it would be highly painful to reconstruct it. So we move to the upper part of the function, and I started a shallow scan process. On the right side, I have opened the structure builder. And here we can see that information about members is collected. During the scanning process, the pseudocode C3 is analyzed. Expressions in which our scanned variables exist are parsed, and information about offsets, and possible type is extracted. If the scanned variable is assigned to another variable, then the latter will also be parsed. All information is represented in the structure builder. Here we switched to another function and started scanning another variable. And this process can be repeated again and again for different locations. And by the way, in the new version of the plugin, it is possible to scan not only local variables, but global too, and even members of other structures. After scanning, so we scanned a little bit and structure builder gained more information. So what does the structure builder allow us to do? Here you can see that potential members get dummy names like field with offset. As the amount of collected information can be quite big, overlapping candidates for being a member are marked yellow. It is possible to select which candidates to keep and which to skip by the enable and disable buttons. Here are solved conflicts by disabling some candidates. They are marked with gray now. This window allows more. We can rename dummy names of members and change their types. Also, we can make some members as array, and the size of them will be calculated automatically. After resolving conflicts, we can press the finalize button and get the final declaration of the structure, which you can see on the slide. As sometimes members don't cover all structure, padding is created for non-existent members. It has type of array of bytes and name gap with offset. After pressing the OK button, the new type is imported to local types. The pointer to this type is applied to all variables that have been scanned. And here is the upper part of the function I showed to you in the previous slide. And you can see that the type of variables has changed, and there are references to the structure member in the code. Here is the code with a sprint function. And now it contains references to members of the structure as well. As you could see, it's quite useful, but what if a structure is really huge and its employment spread amongst many functions? While I was developing the shallow scanner, I came to an idea that I can use this process recursively. While we are scanning a variable, why not to scan every function to which this variable is passed as an argument to? So I've done the deep scan variable feature, and here how it works. This is a function where A1 and V2 are pointers to the same structure as in the previous example, and this function is some sort of call graph tree root. So you can see that the structure pointer is passed to many functions, so we should apply shallow scan to them too, and in those functions we would see the same picture, because here is what the call graph looks like. And here we start a deep scan variable process and wait until it produces results. It can take some time, and in this example it took about 1 minute. And here you can see that the amount of results collected during the deep scanning is far more than in the previous example. After scanning, all functions visited during this process are shown in the output window. They're represented as a tree. I had to solve one issue when making deep scan. When function is decompiled and functions that are called by this function are not decompiled yet, some arguments of those functions could be absent. So the deep scan wouldn't go that deep. And in order to overcome that issue, all call graph functions from the place the deep scan process started are forcibly decompiled once. And it can take additional time, but this process occurs only one time per session. That's something that should be thought about what to do with this. As you could see in the previous example, we have too much information about the structure. There are a lot of members and a lot of potential candidates for each member. And after facing this picture many, many times in my work, I decided to automate the member selection process. So here are results from the previous deep scanning. And after pressing the resolve button, we can see that we have no more yellow color. Resolving conflicts feature works by comparing overlapped members according to the preference table hidden inside the plugin, and it is possible to change it. By default, types with dword, char pointer, etc. have high priority than weird types like signed, int16, and so on. It is normal practice to see them in IDEM. And of course, I gave non-default types like socket, handle, etc. the highest priority. And here is a view of somewhere in the middle of the structure where there are a lot of function members. And here you can see conflicts have also been resolved. To compare function prototypes, I didn't find a better heuristic than to compare the length of the signature. No, but actually it doesn't matter which members we keep, as we can change the type very fast by using recast feature. I'll talk about it later. This feature has its faults. Here we have plenty of character buffers, and I don't know a way to decide programmatically which to keep and which where they start and where they finish. So they should be resolved manually, as I did on this slide. Using the deep scan feature, we can achieve a broad coverage of places where the structure is used, but we might still miss some members. As you may remember, they have dummy names like gap with offset, and there is a way to define a type and name for those skipped members without spoiling the structure in the process. If it turns out the structure is not big enough, just add dummy gap field to the end and use the same create new field feature. Here is a function which hasn't been scanned yet, and there are a lot of accessed dummy members. And to recreate that type, we would have to create new gaps and recalculate their sizes, and all that work should be done with not very handy IDEPRO local types and structured definition windows. It's an error-prone task, so I decided to automate it. So let's create a member from this gap. Here we choose the Create New Field menu. And you can see the window where we can paste a new member type and name. It can be an array of elements or any other type you may choose, and all necessary checks about its size and whether it overrides other members are implemented automatically. And if everything is fine, the structured type will be changed. Here you can see that the new member was created. And here we'll do the same for the line that marked. There are a lot of gaps there. And as the new member was created, you can see that gaps around the new member were also changed. And here I created new fields for every gap. So, okay, now we've learned how to create structures, but you may ask, what is the point of having all those members with the default names? Of course, it's more helpful than just random pointers dereferenced with random offsets in our code. We can at least distinguish one structure from another. But how to understand the purpose of structure members? It is kind of main challenge of reverse engineering. And in order to solve this, we need to know how members are accessed, where and how they're used, and for that, cross-references will be of great help. There are two ways to see them when you're using my plugin. First, we have cross-references during structure reconstruction, while the structure hasn't been yet created. And second, we have cross-references system for members of existing structures. So let me start with the first. While creating the structure, we may make double-click on offset in structure builder of interesting candidate and see the list of sources of the information about that candidate. Here I clicked on another candidate and got 40 places where it was used. The information has function name, variable name, and address of expression. And here, after selecting the member, we move to the place where it was used. That's nice and helps quite a lot, but the code we reverse engineer is usually quite complicated. Structures can be entangled with each other, and we usually cannot understand how one structure is organized without understanding the organization of the others. Piece by piece, we collect information about several structures. Unfortunately, my plugin allows reconstruction only of one structure at a time. And if we start reconstructing another, information about cross-references will be lost. I didn't want to make support of reconstruction of several structures simultaneously because it makes the plugin and work with it overcomplicated. Luckily, I had another bright idea. So here is the code after reconstructing the structure. And I thought, what if just collect information about how members are accessed in the background? It looks simple, but it took me about half a year to realize that it can be done like this. And with my plugin now, each time the F5 button is pressed and decompiler works, my plugin parses C3 and searches for the members' references. That information is saved and can be displayed to the user. So here we pressed hotkey for the member from the previous example, and we see a nice list of all places where it is used. By default, IDA shows member cross-references only from one function body. So my information shows info about type of access, whether a member was written, read, or passed as an argument, and also a line of code containing our member. And I think this feature greatly improves reverse engineering process. And now it is a lot simpler to sort out how program works. As you remember, every variable that was used during the shallow and deep scanning gets type of new structure. And when it gets this type, the decompilation process takes place. And the decompilation process leads to caching information about cross-references. So the more variables are scanned, the more cross-references we get. And a new question arises, how to find where the structure was created so that we could apply deep scan and get as broad coverage of the structure as possible. For that, I am in the middle of creating a feature that helps to find where the structure was allocated. So here is the code in which we would like to find the origins of variable A1. And we selected guess allocation menu. And here you can see where the originally allocated value was used. It also shows the type of allocation, whether it is stack, heap, or global. And now we can go to each location, apply the deep scan process, and achieve a pretty good coverage. And I'm going to alter this view so that it will show a list of places where it is better to start scanning instead of just giving a list of places where allocations were made. and I want to make it possible to find a constructor. In the future, you may expect that this feature will be improving. That's almost all about reconstructing. Later, there will be a little more information about object-oriented code peculiarities, but now we are going to talk about another issue. As we go through the reverse engineering process, we change the decompiler output, and it takes a lot of effort to synchronize types of variables, members, and function signatures. For speeding up synchronization, my plugin offers a recast feature. Every time we have two sites in some expression where each size can be local or global variable, or argument or return value of function signature, or member of the structure, it is possible to right-click or press the hotkey and give both sides of the expression similar types. You may choose which type they get, either from left to right or from right to left. So we shouldn't do a lot of copy-paste anymore. The new version of the plugin supports a tremendous amount of the situations where it is possible to make a recast. There is even a recast for snprint function. So it is possible to use the size parameter and create an array. So, and this feature is not tied to a snprint function and works for any function. And here I have made a recast for some from function to member. So actually, I don't know how to show this feature, and I hope you got what I meant. There is almost the same problem with renaming variables. As we gave a meaningful name to one variable in one place, there are a lot of other places where variables or arguments may have the same name. The plugin allows throwing a name from one variable to another using a hotkey. And now the plugin has the name propagation feature, which allows renaming a bunch of variables. So the name propagation feature does the same recursive traversal over functions as the deep scan variable does. But this time all elements which have a connection with the selected one receive its name. It is possible to rename or use names of both local and global variables and structure members too. And here I renamed a member by function name. By the way, if we have a member with some name and there is a function in IDA with the same name, with my plugin it is possible to navigate to that function by double-click. And by default, plugin propagates names only over default names, but there is a setting that allows us to rewrite the already modified ones. So now let's switch to another topic, object-oriented code. Mostly classes don't differ from regular structures, and everything that was said before can be applied to them too. But the classes have new entities, namely virtual tables and virtual functions, and my plugin is capable to detecting and creating virtual tables, and besides, it enables something more. So let me show you. Here is some constructor, and it has virtual tables. And here we made a scan, and you can see the results in the structure builder. Virtual tables are highlighted. If double-click on them, and window will open with all methods from the virtual functions. So here is the window. And it is possible to visit those functions, and after visiting, they get marked. As you remember, the more places we scan during reconstruction, the more places with the applied class there will be, and the more cross-references we gain. And cross-references will help us to understand structure organization. So in order to help scanning virtual functions, I added option scan and scan all to the menu of this function. And it is quite obvious what they do. But be cautious, as sometimes a compiler doesn't act in accordance with this call convention due to optimizations, and the plugin might produce their own results. I mostly work with C code and don't have enough information about how often that happens. So here is the slide with the results of scanning a couple of methods. And here the results after scanning the whole virtual table. So if we can scan virtual functions, why not to make scan of returned value of the constructor too? The constructor can be called in many places, and going through all of them and starting scanner is obviously possible to automate. Here you can see that some constructor is very popular, and it was called more than 500 times. And we can scan every variable that receives a value returned by this constructor automatically by the deep scan returned value feature. So after finalizing class creation, all virtual tables are also added to the local types, and you can see that they have function prototypes. Unlike Hex Code Explorer, which creates just dwarfed with name types. As I said, when members have the same name as some function, it is possible to double-click them and explore what's going on there. Also, we want to rename functions from meaningless sub with offset names to something more sensible. And here we've got a problem. Names in virtual tables created in local types are not synchronized with IDPro functions. For solving that problem, there is a special window named classes. And it looks like this. It is possible to rename function here, and its name in code and in virtual tables will also be changed. And this window also enables changes in signatures for every method by one. And one more opportunity is to massively change the first argument of methods to class name pointer this. So probably it's useful. There are some other minor features my plugin offers. Among them, I would like to highlight a possibility to automatically rename functions in IDA using rudiments of assertion statements. Sometimes they exist in the code. Also, Hex-RaySpy tools allows us to insert containing record macro in places with negative offsets. This macro is used quite extensively in Windows drivers and Linux kernel models, and Hex-rays usually produce ugly code when faces to them. My plugin can assist in transferring reverse engineering process between different binary versions. If you have a lot of reconstructed types that do not differ from the new version, you can use recognized shape for finding the appropriate type. If you have a number in your code, it is possible to create a list of structures that have the size equal to that number. And then you can select one of them and the number in the code will be replaced with size of macro. Another possibility is to switch then else conditions in if branches. And there are some simplifications for if then branches going under the hood, but it seems like the 7th version of IDA does it on its own. There is also a feature that builds a dependencies graph of structures. So if you are interested, look at README file and you'll find out more. In the latest version, after spending time on refactoring, I singled out the part of the plugin that is responsible for C3 parsing and monitoring for assignments into a separate model. It is now possible to make some sort of data flow analysis using Hex-Rays API. If you want to explore what is done with some variable or where from something came into it, then you might look at my API. In my experience, it's mostly helpful to analyze which which values function arguments can get. For example, I had the device where SNPrint had the same buffer for input and output. And I needed to find all places in the code with those conditions in order to understand whether I trigger it without authentication. And using this API, it is much easier than writing a script with Hextrace API from the scratch. So this API is just 4 classes for all sorts of visiting, and they're used either through inheritance and overriding one or 3 methods, or through set callback function. I extensively use Hextrace PyTools in my work, so you may expect that it will be developed in the future. And here's what I'm planning to add. First of all, I want to add inheritance support, since I have a tricky idea how to implement it in spite of being limited with C-like structures only. Also, I'd like to add scanning negative offsets. They occur in object-oriented code with multiple inheritance. Implicit maintenance of cross-references to virtual functions would allow us to see them through the regular IDA windows and API. And I would be glad if I did that work. And I have a far goal to combine guess allocator feature with deep scan to fully automate the structure reconstruction process. In addition, I would like to update README so that information about how it is used wouldn't be not only in my head. Descriptions that it has now are for half a year ago version. So, as you have seen, Hextrace PyTools supports structure reconstruction completely from its very creation to the stage when there is a lot of structures made afterwards. And it makes reverse engineering a more pleasant process. So if you have any questions, you may ask. And by the way, pull requests are welcomed. And if you have interesting idea about how Hextrace decompiler can be enhanced, we may also discuss that.